So here is the question that I asked at the end of the first part of this lecture. So to figure out the total electrical force acting on charge 2, we need to know the directions of all the electrical forces acting on it. We know the direction of the electrical force that 1 exerts on 2, but 2 and 3 must be interacting as well, so there must be a force that charge 3 is exerting on charge 2. Which way is it? Well, charges 1 and 2 are repelling each other, so they must have the same sign of charge. We don't know whether it's positive or negative, but we know it's the same sign. And 1 and 3 are attracting each other, and so they must have opposite charges. Well, that means 2 and 3 must have opposite charges, so they must be attracting each other, and so they're exerting forces on each other that look like this. So the force that 3 exerts on 2 is down in the diagram, and thus the right answer is going to be the sum of these two force vectors, or in other words, B. In an earlier video lecture in this unit, I charged 2 aluminum-covered ping-pong balls, and they repelled each other. And let's use a situation like that to figure out how much charge we actually would have transferred to these balls. And this will give us an idea of the orders of magnitude of charge we're often dealing with. So first of all, note that if these two balls were in contact with each other when they were charged, they would have shared their charge equally. And so there will be some amount of charge Q, and it's the same on each of these two balls. And now, although I didn't charge them enough that they stood out at an angle of 5 degrees from each other, I easily could have. And so let's take these figures, this distance between them, which is about right from the picture. This is about right for the inertia of one of these balls. And I'm going to use Coulomb's law to calculate the force, the electrical force that they exert on each other. Now note that that's not quite right, because the distance between them is not large compared to their radii, and so they'll be polarizing each other, and Coulomb's law will not really apply. And so the answer we get will be rather approximate. If the balls are hanging stationary, this is a nice static situation, and the equation of motion will work. The vector sum of forces on each ball will be 0. So let's go ahead and draw the free body diagram of one ball. I'm going to work with ball 1, and then write the equation of motion. There is certainly a gravitational force acting on the ball, and there is a contact force being exerted by the string, and it's at a 5-degree angle from vertical. And then there is an electrical force that ball 2 is exerting on ball 1. And the acceleration is 0. Note that this is a constant electrical force pointing in a constant direction because these two balls are not moving. And so I'm not going to have to worry about the unit vector r21. If I was worrying about it, it would be a vector pointing this way. And so the fact that this force is pointing in that direction means I've already taken care of that. So now let's write the equation of motion. So as usual, I'm going to break it up into x and y components. And so before I proceed, I can see that the one force I'm going to have to break up into components is the force exerted by the spring. So let me do that before I write my equation of motion. Here's my diagram for getting those components, but I'm going to just simplify my notation first because I only have one contact force, one gravitational force, and one electrical force. So now, finding the components of this contact force, I can see that the x component here is the opposite to the 5-degree angle, and so it will be just the magnitude of the contact force times sine 5 degrees. And similarly, so now I can write my equation of motion. My x, I simply have Fe minus FC sine 5 degrees. And I suppose there really should have been a minus here. And in the y, all I have is, and everything is static, so the acceleration is 0. So far, so good, but let's strategize for how we're actually going to get to what we want. We want to solve for q. And so far, q isn't in any of our equations. However, we are modeling Fe as being k QQ, right? It is the charge on the target times the charge on the agent, but those are both just Q, so I'm going to have KQ squared over R12 squared. That is Fe, and so once I put that in here, I have equations that I can solve for Q. So my other unknown is Fc, but I have enough equations that I can get rid of that. So I am now going to solve, and you should work through solving yourself. Remember, our target is to solve for q, and there is no point plugging into numbers until you have an expression for q. So before plugging in the numbers, note that we want everything in meters and kilograms, and I have plugged the numbers in and got an answer, and I've written it as in coulombs, but we'd better check that. And if you're not already in the habit of checking your units, you really should get in the habit, because we will have many more unfamiliar units this term than we did in Phys 1104. So we have kilogram meters per second squared times meters squared in the numerator, and we have Newton meter squared per coulomb squared in the denominator, and that's all under a square root. And I'll note that kilogram meters per second squared is a Newton, and so the newtons are gone, and we have meters squared and meters squared, and so we have 1 over coulomb squared under a square root. That is indeed coulombs. And so we get an answer which, to 1 sig fig, which is all we really have, is 3 times 10 to the negative 8 coulombs, or about 30 nanocoulombs. And if you don't know your nano, micro, and so on, get to know them, because we'll have a lot of them this term. Nanocoulombs, or tens of nanocoulombs, turn out to be fairly typical for objects that we charge by rubbing and so on, that are on about the scale of things that you can hold in your hand. Let's now work an example where we have to deal with these unit vectors. And so I've made up an example here with 3 charges, and we're going to find the total electric force on charge 1. Before starting, it's good to just think and draw a diagram, because the total electric force on charge 1 is going to consist of a sum of 2 forces. There will be a force that 2 exerts on 1, and 2 is repelling 1, so that force will be in this direction. 3 is attracting 1, and so it will exert a force in this direction. And so the total force is probably down and right, although depending on the sizes of these forces, it might end up being down and left. Now, let's just write what the expression would have to be. So I'm going to write Fe total as the total electrical force that we're looking for. And it is certainly a vector sum, like so. And we can furthermore just write it all out in terms of Coulomb's law. Like so. Well, we know Q2 and Q1 and Q3. I have them written down here. Let's start collecting other things that we already know. R21 is easy. R21 is right here, and it's just 3 centimeters. R31 is right here. Now, I will admit that I've deliberately made this easy, if you look, I've made a 3, 4, 5 triangle. And so this is 5 centimeters. But in general, you could just get that by doing Pythagorean theorem if it wasn't such an easy situation. So we now know R21 and R31. Now let's get R21 hat and R31 hat. Now R21 hat is very easy because it is a unit vector pointing in the direction from 2 to 1, which means it's just like this. Here is R21 hat. But that's just a unit vector pointing in the positive x direction. So R21 hat is none other than I hat, and we're done with it. R31 hat points this way, and so it'll take a slight bit more work. But here is the trick. The trick is that you can always find a unit vector if you already know a vector pointing in that direction, and you simply divide that vector by its own magnitude. Well, R31 is a vector that points 3 centimeters to the right and 4 centimeters up. And so R31 is just 3 centimeters I hat plus 4 centimeters j hat. And the magnitude of R31 is what we already know. It's 5 centimeters. And so there is R hat 31. It is just 3/5 I hat plus 4/5 j hat. There we go. So we can now easily write out this total force because we have all these numbers, and so I will now do that. I have plugged all the numbers into that expression, and note that tens of nanocoulombs comes out to 10 to the negative 8 coulombs, and centimeters is 10 to the negative 2 meters. And so this part here is the force that 2 is exerting on 1, and this part here is the force that 3 is exerting on 1. And so just plugging in the numbers, I get this, which simplifies slightly to this. And so the point is that calculating the unit vector is actually rather simple, because you can just write down a vector pointing from 3 to 1 very easily, and then divide it by its own magnitude to get the unit vector. It's good to check that we've got what we expected to make sure that we haven't made any sign errors. I said that we expected the outcome to be down and right, or maybe down and left, and if you look, we've got something down and to the right, so that's agreeing with our expectations. And notice how, because of the way the positives and negatives in this expression work, all the directions have been taken care of for us. This negative produced a positive, and so this force due to charge 2 ended up to the right, as it should be, and here we had a positive and a negative, and so we ended up getting a force in the negative R31 hat direction, which is the direction we've drawn.